Welcome to our lectures on DC microgrid, and today we shall discuss about the power electronics converter in microgrid applications. So, this will be our presentation layout, that is power electronics converter interfacing applications, AC to DC converter, which we have seen so many places. There will be a AC to DC converter, essentially it can be controlled or uncontrolled rectifier, pulse width modulation technique for the voltage source converter, 3 phase PWM voltage storage converter, thereafter multi-level converter and its topologies. These will be our course content today. So, in a DC microgrid system, it is very important to analyze how electric power flows between AC and DC network. So, you have to see that. So, there is the interconnectivity between AC and DC and how power flows. The smart DC grid system can be designed based on bidirectional flow, in which electrical energy generated by some RES such as PV panel or fuel cell can be transferred back to the AC grid to support the AC grid. So, this is we require to understand. If there is excess of power, then power can flow back DC grid to AC grid or the main utility grid, and power may come when there is a power deficiency of the DC microgrid from the main grid. Thus, in order to analyze the interface issues between AC and the DC grids, different AC to DC topologies can be considered and it will be discussed now. So, this is overall AC to DC converter and rectifier. As this is a figure 1 of AC to DC converter can be classified between the topologies working on low switching frequency. These are line commutated, these are mainly thyristor driven converter, and other circuit will operate at the high switching frequency like IGBT and maybe the MOSFET of silicon carbide. So, this is a rectifier. Ultimately, if it is a line commutated, if it is uncontrolled, then you may have a diode, but considering the THD, you may have a multiplex converter, that is actually you play around with your transformer. You have a 6 pulse transformer, you have a 12 pulse transformer, and accordingly THD will go down. Students are requested to see my courses on the advanced power electronics, that aspects multiplex converter has been discussed in details. Same way it can be controlled, then it is thyristor based, and so it is the multipulse converter, same thing, it is just controlled, and thereafter we can have a dual converter where AC to DC and DC to AC both the conversion are possible. And another can be your power factor corrected entry point, so that you do not inject power quality issues like problem of the THD into the system, and it can be classified in the 2 categories. One is one directional power flow, that means power flows from the AC side to DC side, and that is called the regenerative, and their boost, Vienna and other topologies are possible. And otherwise, you may have in the 3 phase case, you have a regenerative kind of thing. So, bidirectional power flow is possible, AC to DC and DC to AC, then it is active rectifier, and it can be voltage source rectifier or the current source rectifier. So, overall this is a classification. Now, you have studied into the power electronics courses, it is just a revision. A simplest line commutated converter used, diode to transform electrical energy to AC to DC. This the use of thyristor allows for the controlled energy flow. So, you can control the firing angle The main disadvantage of this naturally commutated converter are the generation of the harmonics and the reactive power. So, you cannot have a control over reactive power generations. So, if you actually change the firing angle, you have a displacement power factor, and thus you have power factor get distorted and reduced, and as well as since it is a nonlinear change, you inject harmonic into the AC system. Harmonic have a negative effect on the operation of the electrical system, and attention should be given to their generation and control. So, we can have a different kind of technique which we have already discussed in my previous lectures in advanced power electronics and control, that is SHE, that is called selective harmonic elimination. You can look at that video lecture, and there you can see that how this THD can be reduced. This is clear that the line current, it is clear that the line current of the line commutated converter, it will be shown in the next figure, is distorted significantly with a lower order harmonic. Generally, if you have a 3 phase 3 wire system, your harmonic content will be 6 n plus minus 1, that means 5th, 7th are the dominating harmonic and so on. Thus, the passive filter can be applied to the DC link or at the front end of the converter to improve the quality of the line currents, or you can have a selective harmonic eliminations. If you it is thyristor control, you can eliminate only one frequency, because you can only have a control over turn on, but if it is a GTO and other full control switches, so multiple harmonics can be eliminated by SHE. Another conceptually different way of reducing harmonic to use single phase or 3 phase PWM rectifier or power factor correction converter. So, you will see that boost topology, and ultimately we require to take the voltage envelope, and current is been forced to remain into the voltage envelope, and students can see that one chip is there, that it is used for the power factor rectification technique is UC 3854 or 5x. So, 385x, it can be 5455 this series. So, that is used for this PFC technique. The most common one is a single phase system based on the direct bead rectifier with a boost converter at a DC link site. It will be shown into this is the figure, and this is the 3 phase version of it. So, there is a challenge involving this 3 phase version with a boost converter, and we can figure stuff getting a current envelope is little bit challenging. The main advantage of the figure 3 of A topology are the improved line current quality and power factor of the system based on the active circuit in the DC link system. Simpler concept has been utilized in the 3 phase diode or the control rectifier as shown in the figure. The main advantage of the converter topology 3B is that ability to control the DC link current and voltage under different load profile. This is a 3 phase system, each diode conducts 120 degree, thus line current can be square wave without any modulated waveform and to improve the line current harmonics. So, this is for the 3 phase, but in 3 phase since it is difficult to generate envelope, we require to but this kind of technique may not work fine, and ultimately we have to sit down with the full control rectifier to get the power for bidirectional way. And actually mostly we may require to put little bit of filters here to eliminate also these frequencies. And apart from that, there are few limitation to it, because power handling capability, since it is one diode rectifier and power handling capability will be very high, and here different kind of topology is adopted. We can have a interleaved boost converter. So, that is also possible, so that it enhances the power quality in terms of the conduction, because if you have a multiple switches shifted by some amount of load. So, ultimately current here does not become discontinuous, and thus you get a better quality ripple and correction become easier. Now, let us come to the pulse width modulated PWM voltage source converter. Now, it is, let us take the full bridge converter. This is the figure A, shows the full bridge fully controlled single phase PWM rectifier, which uses full control power switches in with the anti-parallel diode. So, current can be bidirectional, while voltage blocking capability is unidirectional, and with anti-parallel diode to produce the control voltage in the DC link. What happen? The power will be rectified here, and you get a control voltage depending on its duty cycle. For the appropriate operation of this rectifier output voltage, here you only get the boost topology, must be greater than the input voltage at any time. So, this output voltage V 0 required to be greater than V s, that is one of the challenge here. So, you are required to maintain this voltage higher. So, what happened here? Once this is the B part of it, when this T 1 and this is the path essentially, when T 1 and T 4 are on. So, ultimately this leads to the this part of the circuit, and other is when T 2 and T 3 are on. So, ultimately you have this part of the circuit, and when you have a short through stage or you have a short stage, that is T 1 T 2, T 1 T 3 or T 2 T 4 are on, that means you short the capacitor. So, these are the different mode of operation, and you can boost the voltage in that way, and ultimately what happen, current cannot change unidirectionally. So, once it is flowing, then current will continue to flow through the diode. Once switch is off, then it will change. So, this is the mode of operation. Switch T 1 and T 4 are on, this is, let us say, is a mode 1 on state, while T 3 T 4 are off state. Then the voltage of this rectifier will be V 0, then we switch it over, T 1 and T 4 are off state, while T 2 T 3 are on state, then you get minus of the output voltage. If switches T 1 and T 3 are on state, while T 2 and T 4 are off state, or T 1 or T 4 are in off state, while T 2 and T 4 are in the on state, then this will be 0. The inductor voltage can be expressed as V L equal to L d I dt equal to V s minus K V 0, and where you have K equal to either 1 or minus 1 or 0. This is the equations. So, if K equal to 1, then inductor voltage will be negative. So, the input current I s decreases its value, and when it is minus 1, then inductor voltage will be positive. So, the input current I s will increase its value, and if K equal to 0, then the output current increases or decreases its value depending on the sign of V s, that is depend on whether it is a positive cycle or negative cycle, and allows to compute the control the input current. So, now let us talk about, we have talked about the single phase converter, now let us talk about the 3 phase PWM voltage source converter. It is well known that the voltage source converter VSI can reverse power flow from the load to the DC link, that means as the voltage source rectifier or VSR. However, a standalone VSR requires a special DC bus able to keep a voltage V0 without requirement of the voltage supply, and this can be accomplished with a DC capacitor and a feedback loop control. We will see it in the next slide. The basic operations or principle of the VSR consists of keeping the load DC link voltage at a desired level value using the feedback control as shown in this loop. You can see that you have a control, since you are boosting. So, you have a V output ref, and you will what is actually, you will sense it and subtract it, and it will be put to the generally PI controller. From PI controller you will generate the reference for the switches, and that will maintain the desired DC link voltage. So, the reference value V output ref has to be high enough to keep diode in a converter blocking state. That is something you require to ensure. Once this condition is satisfied, the DC link voltage is measured and compared with this VORF. The error signal generated from the comparison is used to the switch on and off value of the voltage source converter. When DC load current is positive, that means it is in a rectifier operation, you are taking power from the AC side, the capacitor is being discharged and the error signal become positive. Under this condition, the control block diagram takes power from the supply by generating appropriate PWM signal for the 6 power transistor switches of the VSR. In this way, current flow from the AC to the DC side and the capacitor voltage is recovered. And inversely, when power required to deliver to the grid, then the DC load current becomes negative, that is inverter operation, the capacitor is overcharged and the error signal has the control to discharge the capacitor, returning power to the main grid. Now, we will talk about the multi-level converter, because there are two reasons of choosing a multi-level converter. One is that problem of the THD, since the inverter generates a square waves or quasi square wave for this 2 level inverter. If you go to the multi-level inverter, then it generates the staircase waveform. Closer to the staircase, more will be the stairs, more will be more close to the sine wave, and moreover rating of the switches can be reduced. Considering that multi-level converters are power conversion system composed by array of power electronic semiconductors and capacitor voltage sources that when properly connected and controlled can generate a multiple step voltage waveform with variable and the controllable frequency, phase and amplitude. The stepped waveform is synthesized by selecting different voltage levels generated by the proper connections of the load to the different capacitive voltage sources. The connection is performed by proper switching of the power semiconductors. Now, multi-level converters are currently considered as one of the industrial solution for high dynamic operation and power quality demanding applications, covering power ranges from 1 to 30 megawatt. Some of the significant advantage of multi-level converter are higher voltage operating capability, lower common mode voltages, reduced voltage derivatives, voltage with reduced harmonic content, near sinusoidal currents, smaller input and output filters if necessary, increase efficiency, and some cases possible the fault tolerant operation. So, you can have a multiple switches, you can connect this point, the pole at positive VDC or negative VDC, and thus voltage can switch over to plus VDC to minus VDC. This is your 2 level, or you may have the intermediate level and at VDC you can connect to this midpoint of the VDC capacitor which is assumed to be 0, and also the negative VDC. So, you have 3 level inverter. Same way you can have this thing multi level staircase inverter, and it is close to the sine wave. The number of levels of the converter can be defined as the number of steps that can be generated by the converter between the output terminal and any arbitrary terminal reference node with the converter. It is a DC link node denoted by N and called neutral. To be called a multi-level converter, each phase of the converter has to generate at least 3 different voltage level. So, this figure shows that some single phase example of the multi-level converter and respective waveform. This is for the 2 level, this is for the 3 level, and this is for the multi-level, and this is for 9 level, let us say, because you can see there are 9 levels. So, we can classify the multi-level converter topologies. Multi-level converter topology can be classified into 2 major groups based on dependent DC sources and structures as illustrated in figure 7. So, DC to AC power conversion, generally we go for this voltage source. So, you may have a voltage source that is multi-level inverters and 2 level inverter. Considering their harmonic content and the device rating, multi-level converter is been preferred, and multi-level converter can be broadly classified into multiple DC source and the single DC source, and in the single DC source you will have flying capacitor and you have a neutral point clamp capacitor, and here multi-level DC source, thereafter cascade H bridge, that are equal DC source and unequal DC source. Same way you may have a current source that can be split to the current source inverter and load commutated inverter. So, this is the one of the diode clamp inverter topology, multi converter topology. It is the best known and established multi-level topologies are the neutral point clamp NPC or the diode clamped, the flying capacitor FC or capacitor clamped, the cascade H bridge or CHB, the neutral point clamp converter are an NPC converter is composed of 2 level VSCs stacked one over the other with some minor modification. We can see that this is the 3 level neutral clamped circuits. So, this is the conducting diode. One of the disadvantage of this topology is that the number of diode is highly increased when level increases more than 4. So, this is the neutral point clamp converters. So, ultimately once you require to generate the plus VDC you will have this, and if you want to generate the minus VDC then S3 S4 are closed, and once you wanted to generate the voltage 0 then both S3 S2 are switched on, and depending on the polarity of the depending on this whether this voltage is more than this or reverse, the conducting diode will conduct. So, note that there are only two signals per phases. The other two switches receive inverted gating signal to avoid the DC-link short circuit. Figure 9 shows the 3 different switching states for 1 phases of the NPC and the corresponding output voltage levels. The obtained equivalent circuit is highlighted to show how the output nodes A is linked to the positive, neutral and the negative node of the DC circuits. Now, flying capacitor, the FC topology is somewhat that similar to the NPC. So, there is a flying capacitor and number of flying capacitor is almost half of the conducting diode. So, this is a one of the advantage that number of flying number of capacitor is less, with the main difference being that the clamping diode is replaced by the flying capacitor, but with reduced number. The 0 level is obtained connecting the load to the positive or the negative bar through the flying capacitor with positive polarity respect to the DC link. Only 2 gating signals are necessary per phase to avoid the DC link and the flying capacitor being short circuited. The inverted gating signals are related to the different switching devices as shown in the figure 10. So, this is the flying capacitor converter, and we can see here how it is conducting. If you wish to generate this voltage, so it is same, but when you try to generate negative voltage, generally the S1 and S3 required to be turned on, but in that case S2 and S3 required to be turned on, and here S3 and S4 required to be turned on, that is same as that of this diode clamp inverter. So, this is the changes, while 0 can be done through, if you are going essentially how you are going, that is also essential to reduce the switching losses, and state transition will occur with the minimum switching state. If you are in a S1 S2, then definitely you will switch it on S1 and S3 to get the 0 voltage. If you are in S3 S4 and to get the 0 voltage, you should switch on S4 and S2, that also give you the 0 voltage. So, you can accomplish different stage of the voltage by 0 voltage switching by one change of state. So, we can have also another important topology is cascade H bridge and our multi-level converter formed by the series connections of the 2 or the single phase H bridge converter. The each H bridge corresponds to 2 voltage source phase legs, and where the line voltage is the converter output. A single H bridge converter is able to generate 3 different voltage level. Each leg has only 2 possible switching state to avoid the DC link capacitor to the short circuit. And one of the disadvantage of the cascade multi-level inverter that it require isolated DC sources. But it has a modulity in nature, you can put them in cascade manner and you can build any of the level you wanted. The 0 level can be generated connecting the phase output to the positive or the negative bars of the inverter, only the first one is illustrated here. So, see that this is the how you can generate the one of the, you can cascade it to the many level. Once this S1 and S4 is closed, you get a positive DC voltage, and once you decided to short this upper leg since this was conducting, so you get a 0 voltage. Similarly, if you switch it off this and also this and this is on, then you get supposed to get the minus VDC. So, this is the way you are going to get the different voltage and you can cascade them. So, you can get the staircase waveform. Thank you for your attention. I am looking forward to your next courses. We will continue with the application of the pure power electronics in the microgrid. Thank you.